Today we're introducing ellipses here. When you're talking about the ellipse, be careful, don't call it just an oval, because an oval is just a very generally round shape that's not a circle, but the ellipse has a very specific equation that describes the points on that ellipse. It is a conic section, so we call it the ellipse. Ovalness just kind of describes generally round things. We're looking at really these 5 critical points. You have the center, of course, in the middle, the focus on either side, that makes them a pair of foci, and then the vertices on either side of that. So this is the major axis. It has all 5 critical points, and it's drawn horizontally in this case. We also have a minor axis, so we will call these points the co-vertices, and it's not listed here, but that's what I'll be labeling it as, okay? So we have a bit more detail in the middle section here. We are going to be placing our ellipse either with a horizontal major axis or a vertical major axis. The way I look at this from the equation is I look to see where the value of the a is. The a squared is always your bigger denominator, so you can see where it's placed on each of these. If your a squared is under the x, well then to me, I think of the x-axis, and we know the x-axis goes horizontal, so therefore our major axis will also go horizontal. If the a squared, the larger denominator, is under the y, I think to myself, how does the y-axis get placed? And the y-axis goes up and down, right? So that means our major axis will also go up and down. The reason why the a squared is representing the larger value of the two denominators is because we use that a to describe the distance from the center to a vertex. So here's a vertex, the distance from that center to that vertex is a. So if you add up the two a's, you get the 2a, and that's the major axis. So the major axis, of course, is bigger than the minor axis, and because that's the bigger value, that means a is the bigger value, which means the bigger denominator is what we assign with the a. That means the smaller axis, the minor axis, is going to be the value of b. So from the center to the co-vertex at the top or the co-vertex at the bottom, that's a length of b. So this is a b, this is a b, b plus b is 2b, so that's the length of the minor axis. Now we also need the focus on here. The focus is going to be somewhere between the center and the vertex. If the focus is close to the center, then our ellipse will be more round. If the focus is closer to the vertex, then it's going to be more elongated and less round. So here we're just saying, let's call it right here. You'll have one on either side of the center. This distance is going to be letter C. Well, we've already used up the A, we've already used up the B, so the next one is C. So the capital C is the center, the lowercase c is the distance from center to focus. And if this center to co-vertex is the B, then that means we have a base and a height, and we can create a right triangle. It just so happens that this being the hypotenuse, we cannot label it C because we already used the C to describe the base of the triangle. And we've already used the B for the height, so what's left over? The A. And it's not just a random A here. It really is the same length as the length of A that we were talking about earlier from the center to the vertex. That distance happens to also be the same distance here. That means when we're using the Pythagorean theorem, it's b squared plus c squared equals a squared. And that's written down here. The terms are in a slightly different order. Instead of a squared plus b squared is now a squared minus b squared equals c squared. So I call that the Pythagorean theorem with a twist. It's a minus sign here because it's the a on the hypotenuse instead of the c. If we have a vertical major axis, well then you have your center, you have the foci on either side of the center, you have your vertices on either side of the center. Now the distance of a is going up and down from the center to the vertex. So again, there's your 2a, that's the major axis length. And then from center to focus is the length of C. And then from center to co-vertex, that's the length of B. So 2b is your minor axis. The last detail is right down here at the bottom. We're going to use eccentricity to measure its roundness. Is it more like a circle or is it more elongated? So this is the ratio. We're going to take the length of C over A. That will give us the eccentricity. And it's going to be a decimal value between 0 and 1. So it could be a decimal number like 0.4. It could be a decimal number like 0.9. If that decimal number is closer to 1 than it is to 0, then it's going to be more elongated. But if that decimal number is closer to 0 than it is to 1, then that means it's more circular. So I remember it this way. The 0 is a circle, kind of. That means our ellipse is going to be more circular as well. So let's look at these examples on the next page. All right, so here's example 1 at the top. There's our standard form of an ellipse. You have x minus 3 quantity squared over 9. There's the plus sign. Y plus 2 quantity squared over 16 equals 1. We're good to go. So I start with the bigger denominator. Here it is. You see the bigger denominator of 16. That's underneath the y. So I think to myself, the y-axis goes up and down. So that means we will have a vertically positioned major axis. That means the 16, the bigger number, is paired up with the a squared. So a squared equals 16, therefore a is 4. The smaller denominator is the b squared. So b squared is 9, so b is 3. In the box here, it's just a convenient way to organize what these numbers represent, because oftentimes it's like, wait, what does the a do? What does the b do? So the a is the distance from the center to the vertex. The b is the distance from the center to the covertex. So what is the c? That's the distance from the center to the focus. So this is our Pythagorean theorem with a twist. C squared equals a squared minus b squared. And the a squared, again, that just comes from the denominator in the original equation. So it's 16 minus the 9. So the root 7 is the exact length. And we'll use a decimal value just to help us with plotting the point. So that's about 2.6. The centers, the h and the k, remember, change the signs when you extract that information from the grouping symbols. So it's a positive 3 and a negative 2. So my center is at 3, negative 2. I'll use a scale of 1s on this grid. So there's my center, and then again we have a vertical major axis, so I'm just using this green line as a reference. I need all 5 critical points on that line. So above and below the center will be the vertices. That's the length of 4. So 1, 2, 3, 4. 1, 2, 3, 4. So you count 4 on either side. And then on either side we need the focus as well. So that's 2.6 above and below the center. And just label each of those points with the letters to represent what it is. The value of b, which is 3, will go to the covertex. So this is to the right and to the left of the center. Once we have the vertices and the covertices, then we can draw our ellipse. Something like that. And then we'll just fill in the details here with these coordinate points. So the vertices, we're only describing the main vertices, we're not describing the covertices. So we have a location here at 3, 2 and 3, negative 6. The foci are also above and below the center, but that length was a root 7, so we're going to represent it this way. The x-coordinate is the same. Because we're above and below the center, and the center is at a y-coordinate of negative 2, we're going to say negative 2 and then plus or minus the root 7. So in other words, we're describing its exact location. We're only using the decimal value just for purposes of plotting the point. The eccentricity now, we'll take the value of c over a. C is the root 7, a is the 4. My calculator tells me that's about 0.66. So it's not quite 0.5, which would be perfectly in between the 0 and the 1. 1 is more elongated, 0 is more round. This is closer to 1 than it is 0, so we would describe it generally as being more elongated than it is round. All right, so we're going to use example 2 here really just to talk about completing the square, and then we'll do number 3 in its entirety, which is completing the square plus the graphing. So on number 2, the main focus here is how do we complete the square to get that into the standard form of the ellipse that we need. So the first thing to do is to bundle up your terms, group your terms with the variables. So bundle up your x's and then bundle up your y's, and we'll put the constant on the other side. So 16x squared minus 32x, leave a little bit of space. Then we have a 9y squared plus 72y, leave a little bit of space, and then equals negative 16. All right, so we've grouped the x's, we've grouped the y's. Normally when we're completing the square, we would try to get a leading coefficient of 1 on that x squared, and we divide everything by 16, but the problem is we also have to get the 1 on the y squared, and if you're trying to divide everything by 9 as well, then you end up with coefficients back on the x squared. In other words, we're not dividing by 16, we're just factoring it out. So factor the 16 out of the x's only. That leaves us with x squared minus 2x, and factor the positive 9 from the y's only. So that leaves us with a y squared plus 8y. Now we're ready to find that magic number. We want to figure out what we're adding to both sides. We want b over 2 quantity squared. So this is the value of b, the negative 2. So divide that by 2, and then square that result. So that's a result of positive 1. But here's the catch. We're not adding 1 to both sides. Because this is inside the grouping symbols, we have to consider it as being multiplied by 16. So it's really 16 times 1, we're adding a value of 16. In the same way with the y's, we want to find its value of b, divide that by 2, we get 4, square that result, we get 16. So we're not just adding 16 to both sides, its value is 9 times 16. So 9 times 16, we're adding 144 on the right-hand side. And now we're ready to factor the trinomials. So we have the 16 in front. This becomes x minus 1 quantity squared. Here in the middle, we have the positive 9 in front. This trinomial factors to y plus 4 quantity squared. And on the right-hand side, that turns into 144. So we have successfully completed the square. But we're still not quite in the form we need for the ellipse. Notice we have to have a 1 on the right side. We have to have these denominators. If I want the 1 on the right-hand side, then that means I need to get this 144 into a 1. So let's divide everything by 144. And what we're doing is we're looking to see how do these coefficients reduce with that 144. All right, so 16 over the 144, that reduces to 1/9. So we have the x minus 1 quantity squared over 9. Then the 9 over the 144, that reduces to 1/16 actually. So y plus 4 quantity squared over 16, and that equals 1. So I'm not going to plot this just because it turns out that with these denominators, it's the same results as what we had previously. We had a 16, we had a 9. The bigger denominator is on the y, so it's another vertical major axis. We're really just using this to talk about completing the square. So let's complete number 3 in its entirety. Here's number 3. So we'll complete the square and we'll graph it all together. So again, we want to bundle up. We want to group the terms with x and then the terms with y. So x squared minus 8x plus 5y minus 30y equals positive 39. Now we remove the common factor. There's no common factor here. There's no common coefficient, in other words. So just x squared minus 8x is what we have. But I'm going to put parentheses here just to kind of create that sense of we're going to have a trinomial in a moment. We'll be factoring that later. Out of the y's, we can factor out a 5. So positive 5 times the y minus 6y, leave some space. That equals the 39. All right, so for the x's, here's the value of b, negative 8. Divide that by 2, we get negative 4. Square the result, we get 16. This is a positive 16. Take that and multiply by its coefficient, which is just a 1. So it's 1 times 16. We're adding 16 to both sides. For the y's, the value of b is negative 6. So divide that by 2, we get negative 3. Square that, we get 9. This is a plus 9, but you have to multiply that by the 5. So its value is really 45, so we're adding 45 on the right. So now we can factor. We have x minus 4 quantity squared plus 5 times y minus 3 quantity squared equals 100. And next, divide everything by 100. So we have x minus 4 quantity squared over 100 because there was no coefficient to reduce that by. 5 over 100 gives us 1 over 20, so y minus 3 quantity squared over 20, and that equals 1. That's our ellipse. All right, so now find your largest denominator. There it is. It's under the x. I think of the x-axis, which goes horizontal, so we have a horizontal major axis as well. The larger denominator also gets paired up with the a squared. So a squared equals 100, therefore a is 10. The larger denominator is the b squared. So b is root 20, which is 2 root 5. But for plotting purposes, let's get a decimal value there. It's about 4.5. And now for the c. So c squared equals a squared minus b squared. So that'll be 100 minus the 20. So our c is root 80. That'll factor to 16 times 5, so that'll give us 4 root 5. And so its decimal value is about 8.9. Our center is at the h and the k, so we have a positive 4 and a positive 3. All right, with that big value of a being 10, we won't have enough space, so let's change the scale and go by 2's. Our center is at 4, 3. And because we have the horizontal major axis, I'm using this green line just as a reference line. I need all 5 critical points right on that green line. So to the left and to the right of the center, we'll find the vertex. That'll be 10 units away. So count by 2's. And we're still off the grid just barely. There's a vertex. There's the other on the left. The distance of C will lead us to the focus, so 8.9 to the right and to the left of the center. You can see here the focus is very close to the vertex. That means it's going to be very elongated. And now the minor axis will go up and down. That's the value of B, which is 4.5. Yeah, you can see it even looks kind of elongated compared with the graph we had in number 1. So here are the other details. Where are those vertices? We have negative 6, 3 and 14, 3. Where are the foci? Again, the foci, that'll be the value of C, and we're using the 4 root 5 to the right and to the left of the center. So that'll modify the x-coordinate of the center. So we have the x-coordinate 4 plus or minus the 4 root 5. And the y-coordinate stays the same. The eccentricity now, that'll be c over a. So the 4 root 5 over the a value of 10. So that'll be about 0.89. So that's quite close to 1, so it's elongated.